Hello, this is Brian Rao with assignment number 6 for the physics class. Assignment number 6 covers the different types of joints. The very first thing I'll show off is the seesaw. So as you can see, it starts off with a pig on one of the edges, and the seesaw falls down on that side. Another pig comes down and applies a force to the opposite side of the seesaw, launching this pig up into the air. The pig knocks on the edge of the seesaw one more time, giving a slight lift on the opposite side. This side falls, the other side falls, and the simulation ends. I'll briefly show that off. Down, up, down, slight hit, fall, and then this one will fall, being a circular object with a small momentum being applied to it. The seesaw, we generate our components, and what we do is we have a revolute joint be our pedestal with our main center bar on top. This allows that bar to move left and right from its center. Moving on, we do the same revolute joint for each one of the seats. We apply that point to the center of each one of the seats, and we use a gear joint to ensure that each one of the seats is always parallel to the ground. And after that, we just add our pigs. So again, it's point here, point here, point here, gear joint, ensuring that this side is parallel and that side is parallel as well. So taking what we learned from that, we'll jump into the Ferris wheel. And the Ferris wheel, right here, is roughly the same idea. We have a revolute joint right here in the center. This has a motor and a force being applied to that motor. A speed being applied to that motor, and there are revolute joints to the center of each one of these pedestals. And they are also gear joints to ensure that they remain parallel to the ground right here. And they just casually go around and around. I can launch my pig, boom, and you can see that without even touching that pig, since I hit the ledge, it was enough to just knock it off its center of balance, and then it would just casually roll over. I can destroy the ledge, as you see, and I'll try and solely hit a pig right now. There we go. And the force that was applied when I hit this ledge was also enough to knock the last pig off its balance, because the force of that hit was applied to the entire system, and you saw the last pig fall out. The pigs, as I mentioned, are balanced, but again, if the system is just slightly moved, they all fall off their center of balance and then just collapse over. So how I make sure that the pigs don't go rolling off as soon as they're created is I make sure that I set its rotation, fixed rotation, to true, and then when the pig collides with the platform, I switch that back to true after the collision takes place, so that way on the next collision, when the bird or any of the system is moved, since the fixed rotation was turned off, that will allow the sphere or the pig to rock around, and that causes it to just gently roll over and fall off. I needed this in order to ensure that that the second that they land, they don't start rolling. So right here, I'll remove that that function, and you can see that they collide when they're placed on, and since the entire system began to move, they just casually roll, and the rolling just gets amplified, and they all fall off. But under this case, you can see that there is no movement until they finish their collision. After they finish their collision, any disruption in the system will be enough to launch the pigs off balance. this can also be modified so that way only the bird itself can knock them off balance, but that's some extra tinkering, and I wasn't sure how detailed you wanted this. But going into the Ferris wheel class, the Ferris wheel, we generate all the pieces, and we place all our pigs on each one of the pedestals. And as I mentioned before, we have a revolute joint that's a motor which spins our giant Ferris wheel. We have revolute joints for each of our sticks to our main wheel, and we use gear joints to ensure that each one of those ledges remains parallel, because if they weren't, our pigs would just slowly roll off the ledge. And that basically covers everything on the Ferris wheel. I wasn't exactly sure how much you wanted for the final, for the second example, but here I have a quote-unquote ATV car, and in this case, what I ended up doing was I increased the torque for the motors and the two wheels. I also used the wheel gears, so that way on a bumpy road, the system kind of acts like a suspension to it, and if the wheels end up getting stuck, the torque would be enough to get it out of any of those bumps. And I just use an enum to basically tell the difference between the two. Our other one will be our race car. Our race car has a lower torque, and on its update has a faster acceleration factor to it. It also doesn't have a suspension system, since it's going to be on a flat surface anyways. It doesn't need to calculate that extra math. But as you can see, it accelerates at a much faster rate than the other one and falls off our screen. But I'll just go really quickly. All cars have the same parts, so we dictate that. And then from whatever type was defined, we either create revolute joints or wheel joints to give our ATV a suspension and more torque or less torque, depending on the type of car. And on the update, we dictate its acceleration by adding the speed, or in the race car's instance, we multiply that speed in order to make it accelerate a little bit faster. I also did place this limit because I did realize that increasing the speed too much, and I think it's around past 60, which is the refresh rate, things start to get really messy, and joints tend to break. So I added this to ensure that the speed is always either on one of its two maxes, in the positive or negative direction. But other than that, I think that covers everything for this week's sprint. Thank you very much.